Good afternoon, everybody. This particular presentation is really more of a scientific comparison to try and understand a little bit about some of the process considerations around and the science application around hydrogen peroxide vapor and really what's termed as the aerosol or dry fog type processes. The reason for such a presentation is really driven through the last year through the sort of PHSS association with regulatory authorities on the challenge in the industry to having what considered can be a more, a less understanding. No robust process knowledge doesn't lead to a robust process. And there's been a challenge in the past where really all the VHP generators and the developments of these products, there hasn't been a real push to share the science behind these developments because there was a consideration in doing so, you were giving away your technology and people would copy it. So you get this general overview of these are the cycle phases, this is how you kill a few BIs, these are the parameters you consider. But really an understanding of the science behind that process, not so much. So to make an informed decision, and in my day job, I work with isolator technologies, rapid material transfers, and VHP is something that we've employed into our processes. We have developed our own completely integrated biodecontamination system, so we don't use any of these commercial generator vendors, but we have designed the process by understanding the science, and that's where we really drive on. So what I'm going to look at is a scientific comparison between the vapor molecule and an aerosol, starting off with really just where it begins. And when you take this peroxide, whatever form it's in, then you deliver it into a particular stream, an airstream, or a volume, and then how does it act thereafter? And really the impact of the molecule comes from the vapor side, and I'll give you the calculation for that molecule size in behind that, in comparison to the aerosol droplet, and that is very much an aerosol droplet which is much larger in size and creates a totally different process right from the beginning. The regulatory acceptance of VHP for biodecontamination of stopper contact surfaces as a sterilization process, there's been a step change last year when regulators have really started to up the ante on challenging the industry to understand a little bit more about the science and this process, and in doing so, not accepting VHP as a sterilization process or even the H2O2 as a sterilant. And that's their starting position. Industry, you respond by giving us a scientific understanding and the rationales to apply in your particular processes. So a little bit finishing on application. So the first thing, if we look at hydrogen peroxide itself, there's two components in there, the OO bond and the OH bond. And these particular components deliver, in comparison, a molecule size once flash evaporated, which is in the pico range, which is 10 to the minus 12. Now, if you compare the micron range, which you get from a droplet from an aerosol, this becomes the first scientific comparison. So to make that, take the maths away and get it into real terms, if you consider the size of a golf ball as pico, the size of the Empire State Building is a micron droplet from a... So here you have two very different starting positions where you get a pico size molecule that can pass through Tyvek and HEPA filter membranes and a droplet which can't. So that's a starting consideration you have to think about. So the next thing is that we have to get in around point contact supports and load presentations. So these very, very small molecules of the vapor do form readily around point contact support. And often in validation, we qualify that with swabs with biological indicators. Do the dry fog aerosols form so readily? They will do in time because you get up to a point of liquid condensation, whatever Tim likes to call it, but you will get a deposition layer on there which will form around, but it's not something that happens readily at the beginning of the process. We also have a world of microbiological challenges, and we validate with clean spores. We have the classic rogue BI, which is a clump of spores which enable protection of the innermost protected spores. You can see the classic football clump in here. So the spores in the middle of that are not going to be decontaminated with a surface agent, whether that's aerosol or whether it's vapor. So we have to manage rogue BIs. We're looking at a distribution. We can get occlusion of biological indicators also by the contamination of biological indicators, so-called rogue batches. That is not a rogue BI, that's a rogue batch. That was only a BI from one manufacturer that was from last year. So these are not old photographs. It still happens today. They're quite difficult to manufacture, these BIs with quality. We have to challenge the efficacy of our processes, and we have to look at, one of the challenges is that primarily the BIs are in a Tyvek primary pack. By definition, a biological indicator is an inoculated carrier inside a Tyvek primary pack. If it's just a naked BI, that's just an inoculated carrier. So an actual BI, if vapor molecules pass readily through the Tyvek, we're in a good starting place. If the droplets can't pass through the Tyvek, then that must indicate a different process. We'll look at that. The actual process or the mode of action is really about free radical attack. And particularly the components of that free radical attack, and the most oxidizing potential comes from hydroxyl, which is a part of the components of hydrogen peroxide, that give you very, very broad spectrum efficacy. So if you look at the oxidizing potential range here, we've got fluorine, which you can hardly even contain. Hydroxyl underneath is very, very close to the top of that. What this actually means is that broad spectrum efficacy. And the real process of inactivation is free radical attack. Now, free radicals are highly energetic, unpaired atoms or molecules that, to exist, they're powered to pair. And in that process of pairing, they're extremely destructive, and that's the kill mechanism. Now, that sort of oxidization effect carries through into efficacy from a whole range of different microorganisms. Now, here we come a little bit of a challenge, because a lot of the peer-reviewed published data out there on all the different microorganisms that are inactivated with hydrogen peroxide are all about vapor. And you suddenly can't start to leverage all the data from a vapor process and say, well, that must be good for an aerosol dry fog process as well, because it was never tested on that. You will have new data to test probably on the biological indicators in activation. You can get rapid kill for good reasons there. But have you got the peer-reviewed reference data from all these different microorganisms in behind it? Probably not. And it's one of the challenges, because my company, Franzil, largest German isolator manufacturer well, the largest in Germany. Our competitors there scan head-to-head on most days, friends today. We're on a neutral platform, so it's a good day to share knowledge together. So basically, from that particular standpoint, we really choose the technology with all the peer-reviewed references, with the science support and understanding behind it. And we've taken a look at chlorine dioxide, nitrogen dioxide, all of those. And as Martin said, hydrogen peroxide is just a bit difficult to beat, because a lot of these other processes chemically derived, and you need a chemical to break it down. Well, hydrogen peroxide breaking down quite easily with catalysts to oxygen and water and non-toxic. That's a great starting position. But there's a huge negative out here for hydrogen peroxide, and the industry's really caught up on that. And that's the development of biological products and this oxidizing potential. And we now need to focus on a lot less than 1 ppm for a lot of the new biologicals. So new analytical chemistry methods have to be developed, and we're learning to manage the process still. So continuation of the science and not jump into another process we know little else about. So, you know, it's always a new kid on the block. Interesting, but do we jump? And really, I've characterized the different processes. As Tim said earlier, you evaporate hydrogen peroxide by flash evaporation. Now, whether that's on a hot plate or as we do on fire bars, whatever, this technology just takes a liquid, which is typically 30%, 35% peroxide, and the rest is water. So you get this solution, which starts as a combination of water and oxygen. And already there's bonds in that liquid that's there, and you're going to start to flash evaporate that. Now, when you flash evaporate hydrogen peroxide, you create these very, very small molecules that are carried in the airstream. When it gets to the volume, then there's a step change wherever you start to build the saturation vapor conditions. So if you stay short of dew point, the old, like the Steris way, I don't used to be another manufacturer, but a way that was indicating it's better to stay dry, to introduce this term, that's short of dew point. And really what you're saying is that, okay, you're not expecting a deposition on the surface of these molecules, you're expecting the molecules to be held in the environment. So you're heavily involved in really reliant on gas distribution and gas concentration measurements. Well, number one, the gas concentration measurements the devices are not accurate enough to be able to really control the process on that. And number two, you've got a random contact of molecules on a surface. If you go just past dew point, you start to lead towards that process of microcondensation, and it's a delivery mechanism. In science, it's just a plain delivery mechanism. And on the surfaces, and you can see spores on glass here, but it's a nuclide effect as well, because you can see the nucleus is the contamination here. So peroxide is forming around those biological challenges, even before it gets the monolayer over a surface. So the kill process is starting very rapidly. And here's the big but, and a lot of people get confused about this, is that the whole process is like spraying something on a surface. Like you take a spray and you get a microcondensation or whatever. That isn't the process at all. What you're getting is saturated equilibrium, vapor pressures, and saturated equilibrium. In equilibrium, we'll get as many molecules arriving on the surface as leaving. So there's a dynamic exchange going on all the time. It's a completely dynamic process. If, conversely, you aerosol or spray onto a surface, that is a completely static process because you've got a deposition and it's driven one way. And fundamentally, that's a really different process from one compared to another. The next thing is when you go over to condensation, or we call it micron deposition, because we don't want it, like Tim, we don't want to see it. You go too far, what does it do for efficacy? And here the study, this first paper I referenced, was done by Bimcox in Germany, was really where they looked at the impact of humidity and whether you should go past dew point. And what they found is, yes, just like Tim said, you need to get past dew point. And I found that years ago, working with different applications there, until we actually got past dew point. There was no reliable decontamination. But this paper showed you only actually need a 2 to 6 micron deposition on a surface. 2 to 6 micron is invisible. 2 to 6 micron also gives you impact if you've got a dynamic surface exchange going on. Because my analogy there is a bit like a deep sea. So you have a deep sea, and you get this wonderful exchange of molecules on the surface. What's happening down at the seabed? Nothing. So there's no added efficacy. And that's really what that scientific paper showed you. This is also an indication that you shouldn't get a preferential condensation because it will add as a water barrier to get any further effect on income and efficacy. Now, even stainless steel is a mild catalyst, so you are going to get some breakdown by surface reaction. So you do need a replenishment, hence is why you need to not get into micro-condensation that's visible, but get into this micron deposition, whatever you like to call it. I tend to just call it VHP these days because apparently you can't register a trademark that's such a common term. You know, you can register Hoover, but you can't register vacuum. So everybody knows what you're talking about when you talk about VHP, but you know, that's how we are. Now, if you look at the process of just getting past dew point, those are all based on physical parameters, physical chemistry. So here you've got injection rates, you've got starting humidities, you've got temperatures. And all those together give you an indication when you get past dew point and into that efficacy range. And there's peer-reviewed published papers exactly on that. But then you start to look at the process of application thereafter. So if you take a dry fog molecule, that larger droplet size, probably 8 to 10 microns, really starts to look at a comparison of more of a static process because you're relying on these droplets delivering onto surfaces. They cannot pass through Tyvek, they cannot pass through HEPA filter membranes, and they don't readily form around point contact supports until there's enough there to actually sort of saturate that location. The challenge of not being able to get through Tyvek provides a different efficacy issue. So why then do when you run BIs with Tyvek, do you get quite rapid kill? Because that just goes away from what James has just said. You know, he just said that small molecules pass through very easily and the rest of them just settle on the surface. Maybe. Let's have a look at that in a minute. And dry fog needs this expansion zone actually to create this aerosol zone that will distribute. And it's often distributed by Brownian motion to get the distribution out there, or you need some kinetic energy. Now, the first thing to understand about hydrogen peroxide is that it's subject to hydrogen bonding characteristics. This means it's poor at passive diffusion. And the reason for that is that the water molecules in the environment are a barrier for distribution. So one of the reasons to dehumidify, we target 30%, because we found at that level, the water barrier is taken away, so the hydrogen peroxide molecules distribute much, much better. So up at 50%. Yes, you can still get enough space in the volume to get peroxide and get your 6-log efficacy, even if you're up at 60%. But you're a lot closer to getting condensation visible because you're overloading the cycle, because classically there's enough efficacy just by a few grams in a cubic meter volume to get decontamination. The extra injection is all about gas distribution challenges, and most of the challenges in all that we deal with and all the process integration is two main issues. One is managing a condensable vapor, not treating it like a true gas, and the other one is in distribution of that vapor in the volume. If you can, in engineering and science, manage those two things, you're going to get some short cycle times. So these aerosol molecules trying to get through HEPA filters start to limit the boundary of decontamination as well. We create our own aerosols by coughing and sneezing. There is an expansion zone. We can see that it comes into it. And a friend of mine used to do a really mean thing at an exhibition. So one of these dry fog companies had a dry fog generator. They had water in it. They were spraying the dry fog out, and you know, that was it. Wonderful demonstration. And he used to go up and talk to this guy and hold his hand over the end of the dry fog generator and, you know, tell me about dry fog and whatever. And thank you very much. And at the end of it, you go to shake his hand, and obviously it's wringing wet. Because in this high concentration zone, why that matters is that it's quite difficult to do low decontamination in a small chamber where you're not got the room to expand. So often in a chamber, it needs to be larger to get this expansion zone than it does with vapor, where you can expand it very, very quickly. Now, the other thing here, you can see that if it's not going through a Tyvek, you're getting this wonderful deposition layer. And that's going to saturate and permeate through. So you've got a reservoir of peroxide that's going to go through and rapidly kill the biological indicator. And actually, that's what happens. So you do get a very rapid kill because you create a reservoir of peroxide to... Is that the real world? Is that what the real process is of inactivating microorganisms on the surface? This is probably not. That's creating a false local reservoir to give you a source to decontaminate through. So it's great for killing BIs, but does it actually represent the process? Are you validating the process? And these are the sort of challenges that we've looked at and we sort of struggle to answer, so we put most of our efforts into decontaminating with hydrogen peroxide vapor and not going dry fog. We could easily use dry fog, but that was a decision-making process my company went through based on science and nothing more than that. The mode of action from hydrogen peroxide itself and this free radical attack mechanism, there's many different mechanisms going on at the same time here. So you can break through the cell walls. You can affect the cytoplasm. You can cleave DNA. So it is used in some facilities for inactivation of viruses. Viral clearance of environmental viruses is an application that's used in biotech. And these reaction mechanisms, they take actually seconds. So why have we taken minutes or hours to do a decontamination when the mechanisms of free radical attack and reaction mechanisms are very, very short? And it all comes down to the presentation of the peroxide and manages in a condensable vapor, reaching the saturated vapor conditions because we want to get past dew point, and then controlling that with good distribution. And those where the challenges come on engineering integration. So these are the slides that just give you the background. And all these references, the peer-reviewed published references, at the end of this presentation, they're all listed. And this presentation is for free distribution through the ISPE. So it's not, you'll all get this. Philip will give you that. So all these references to, this is about bacterial cells, but all these mechanisms that we now know and understand, a lot of those are based on vapor. Can you translate that to a vapor process just because it's got hydrogen peroxide in it? That's one of the questions we challenge ourselves. Now here, look an application as well. This is our application where Franz Zeil taken this technology. So we take hydrogen peroxide, classically, 35%, the rest of it is water in a solution. Medical grade is a particular sterile grade, they call it, and that means the components of that hydrogen peroxide haven't got very high levels of other contaminants in there. There are and would be filtered out because it's delivered through filtration systems, but they actually damage the vaporizing bar. So you get, if you don't control the quality of the peroxide, you'll get a high maintenance cost because the hot plate or the vapor system will be damaged. You flash evaporate for whatever system you have, and essentially that creates these pico-sized particles, very, very small particles. They're delivered into a vapor stream, and primarily what we found is that it's very inefficient. I think Martin alluded to earlier. If you inject above a HEPA filter and try to get the peroxide through to build process lethal conditions in the target area. So if you can go direct injection, then you can build rapidly process lethal conditions without the restriction. Now we need, in the pharmaceutical industry, to take all risk out of where the containment boundaries are and where the contamination aseptic boundaries are. So we need to take the vapor through return air ducts and other places to make sure that we have a very secure boundary. A HEPA filter is never a single plate or membrane. It's a labyrinth. It's not a surface. So to get penetration through all that labyrinth, you need to actually pass vapor through it. Putting a BI on the surface of a biological indicator on the upstream side and saying that filter has been activated is some data, but it's not assurance for sure. We now need to go through this mechanism where we create the saturated vapor, we get the deposition, we get the free radical attack, and then the focus goes on into aeration time. Because with direct injection technology and some of the filling lines that we build now, 10, 15 minutes, that's normally the range, 6-lock efficacy kill across the whole line. That's it done. By the time you get into the decontamination phase, you've got all those biological indicators done. Where the cycle time is longer, it will primarily be because of a gas distribution challenge, not because we've reached process lethal conditions. After that, we need to focus on the aeration and the integration of catalyst cells. Now, we have impregnated cloth catalysts, which we use in our circuits. We motor them in and out of circuit. So we drive them into circuit when we require them and drive them out when we don't require them. And it gives you local catalytic breakdown without the need for huge air handling systems to try and get the airflow up. Just use air for pressurization. That's all you should need makeup air to be. The rest of it you can deal with locally through catalysts. We need to target less than 1 ppm. Classically, most biologicals, you'll start at 0.3 and go down. That will be your target endpoint. And that requires us to look at totally different cycle profiles here and understand that we've got these different phases. So here we have this gas phase where we're first getting the molecules into the environment. We're building to saturated vapor conditions, and then we get this micron deposition, which, as I say, is dynamically in exchange. The rate that we build that concentration is a rate phase of, there's a transition event going on here. So there's two different vapor pressures between water and hydrogen peroxide. Tim alluded to that. So consequently, there's this transition event. When you flash evaporate, you get whatever the concentration is off the vaporizer. The vapor pressures take predominance. So when it gets into the isolator volume, peroxide starts to condense first. So primarily you get a higher surface condensate, up to 70%, and that's a real kick for kill. Now when you get into equilibrium, which doesn't happen, it happens quite shortly thereafter, consequently the equilibrium, if you started with 35% concentration, the equilibrium is 35% concentration. The condensate on the surface is 35%. That's the equilibrium state. When you flash evaporate, if you've had a lot of microcondensation on the surface, you will get this peak. If you manage the surface deposition to be very, very small, just the micron layer, you don't see so much surface condensate come off the surface. Those big peaks and one of the challenges that Tim will have if he's working with some of these generators is that with just 2 injection rates and adding a bit of overkill, you can't stop overwetting a little bit because you're going on past the time you need efficacy, and all that added overkill is for gas distribution. It's overkill because we need to add overkill. In the ZIL systems, we have 4 injection rates, so we'll be able to manage the vapor deposition a lot better without overwetting and an overkill, backing it off and just ticking it along very nicely. But look at this profile here, similar to one that Tim showed the other day. It's not the classic up, flat, and back down again. The kill is all done before you can get into the long plateau phase. So why? Yes, we could extend out a nice plateau, but it's done. So why do we need to start thinking about different profiles of efficacy and how they're demonstrated. Those gas distribution profiles are also a fingerprint of the cycle. And we've characterized some control points on that cycle where we use software to analyze to do a system check of validity of the cycle before we process to the next one. Again, that's quite unique technology. Now, firstly, the most exorbitant materials in your isolator systems are the HEPA filters. So classically, we use PTFE HEPA filters these days. There's been a huge development in those, and they've been hugely effective in applying to isolator technologies. PTFE is hydrophobic and a really good starting place. We focus on 2 kill phases. One is kill phase 1, where we use the direct injection technology, above and below any air distributions, so filter membrane, CG screens, stainless steel perforated plate, whatever does the air distribution to get a really unidirectional airflow, we inject above and below that. So we can build to process lethal conditions rapidly in that first phase of kill. But we want assurance that the HEPA filters and the return air ducts are decontaminated. So in the second phase, we get in recirculation effective. So what we've done here, we've taken a very high gas concentration and we've injected it through rotating nozzles. Here's some CFD modeling on the rotating nozzles, because each of the nozzle designs we design for volumes by computational fluid dynamics. This expansion zone, expansion is cooling, so the vapor needs to be not condensed before it arrives into the target area. So basically you do that by heat tracing or managing the heat distribution on that. So if you hold the peroxide high concentration, 2,000 or 3,000 ppm coming off of a vapor phase evaporator, if you hold that up above a certain temperature, it's not going to condense en route. So that means when it gets into the volume and it starts to expand into the volume, that's when it starts to deliver those micromolecules onto the surface. And key to get right down into the corners. These are actually rotating. It's just a cut of a CFD model just to show it's reaching where it should reach, and then that starts to rotate and spin around the whole volume. It means you have classically in this phase 2 plateaus. I've emphasized it here with this longer graph. The plateau 1, kill phase 1, change the injection rates, get the recirc fan going, plateau 2, and then your classical exponential reduction. That is a good BI with spores, an SEM, a scanning electron micrograph, taken at the edges. So that clumping of spores at the edges should be no problem with any biological process dealing with vapor systems. That is a bad and rejected lot of BIs where there's so many layers of spores that have clumped at the edges, and that has been a real challenge to inactivation. That was a failed lot of BIs because they were consistently of that quality. Now, you can do sort of system d-value, enumeration checks, classical, but these SEMs do really reveal what the quality of the BI is. And my team of microbiologists, and the 4 of them in Germany, each of them have been trained to do SEM analysis at a local institute. Now, these SEM scan electron micrographs cost 1 or 2 million each, so there's not something you have on your bench. So you can go to their facility. But you can't send your BI to have it scanned by an analyst who doesn't know what he's looking at. So you need a microbiologist that knows what they're looking for and really target the BI and respond to what they're seeing. So vapor injection is used with direct injection technology to find this lethal. But we're also getting this expansion zone, which is expansion is cooling, so 50 degrees one side of the nozzle. Within a very short distance, you're down to 25, 27 degrees, low temperature process. It's rotating, so no hot spots are created by the incoming jet. It's rotating to create turbulence. So if you create turbulence, you've got the perfect conditions for molecule exchange on surfaces. As soon as you get into unidirectional airflow, trying to distribute by air, fans, recirculating, where it speeds up across the floor to the return air ducts, that's where your risk of positive BIs are, because fast airflow across surface doesn't help the molecule exchange on the surface. That's known as well. We get this classical deposition phase that we really need to focus on to be as effective and as short as possible. We don't want high saturation. We don't want materials absorbing. We don't want saturation there, because all of this adds to aeration time and ineffective cycles from point of view efficiency. Now, when we're starting to apply these technologies, so we see now a mixture on filling lines of combinations of RABs and isolated technologies, and both manual and vapor decontamination. So this is a filling line for pre-sterilized containers. So this first part with this NTT, no-touch transfer process, is just using manual disinfection but again, it's grade B, it needs a sporicidal agent. And hydrogen peroxide, as impregnated wipes, are often used these days. Spraying alcohol around, that's not sporicidal. So putting in some of the really aggressive chemicals that can damage stainless steel, so peroxide impregnated wipes have become really quite effective in these areas. You've got in the main line here now, this is air intake and air. This is just for aseptic fill-in of a non-toxic product. So we can take air from the room and deliver it back to the room. This system has no support air handling systems, no standalone generator. Everything is on board. That is installed into the fill-in, into the clean room as you see it. There's no other support systems. The biodecon system there is all on board. The catalyst systems that are motored in and out of circuit are all on board. And that's what, this is a 1.5 hour cycle time down to 1 ppm. When we got down to 50 parts per billion, we're talking 4 hours. It just take a little bit longer there, but primarily that's the sort of targets you can get for filling lines these days. And yeah, alternatively to like the E-beam that Manfred showed earlier, no-touch transfer is developing significantly. Of the next 30 projects I know about, they're all no-touch transfer, and one is E-beam because I think Manfred's a really good salesman. But this technology has got to be connected with and tied with. And the reason I've put in this slide, because there's nothing to do with the VHP side, I started with VHP. I started with a line for Rhone Prolink Rora doing 6 tubs per minute of pre-sterilized syringes in a VHP chamber. It was then I found that this dry process didn't really work until one famous day when the heat tracing failed on this tunnel and I got condensation and all the BIs died when I'd had so many positives before. I realized that you basically, like Tim says, you need to get past the dew point. But what I also found, in those early days, you put peroxide, it goes through Tyvek like it's not there, you will have a residual in that syringe. And classically, you will have 0.5 ppm remaining in that syringe after the aeration process, because it doesn't come out. And that drove E-beam technology. We had to, in the industry, look for another solution. So importantly to understand that these technologies, I wouldn't put hydrogen peroxide anywhere near pre-sterilized containers. And I do know some of these rapid decon chambers have been put in 2 lines using pre-sterilized container transfers. Some companies have recommended that approach. And I do know of 2 of them have been taken offline because issues of residuals. This other big argument about VHP as a sterilization process or not, the term sterilization was coined years ago by Steris, and it's now a bit of a misnomer. It's not a sterilization process. That is in the pharmacopoeias as classical penetrative process. At best, we can achieve surface sterilization. And then we saw this argument in the regulatory industry between VHP is not a sterilization process for feeder bowls, stopper bowls. You need to autoclave those out place, and you need an autoclave sterilization process. That's what you must have, because VHP is not. But we need, and in the PHSS working groups, we needed to think about, well, what is the process actually? The process is if we autoclave these feeder bowls, we'd have some Tyvek covering on them. We'll take them into now a grade C clean room, because that's the pathway to the isolator, which is in a grade C background environment. We'll stage them for a period of time in the grade C area with some wrapping on. We'll open the isolator door and we'll assemble those feeder bowls, probably with the last Tyvek cover still in place. And then we'll take off that cover very quickly and we'll close the door and we'll complete a VHP cycle. Is that absolute assurance that sterility has been maintained on those stopper bowls? No. How can anybody claim that? So VHP then has to re-establish surface sterilization. That's the science of the process. But it's a real key point here. It can do that if the bioburden is really low. So if you can control the bioburden to be really low, then that works. So you do need this controlled procedure from autoclaving through. And the PHSS, through its guidance initiative, are preparing this guidance on this complete procedure and how that's managed. Because even the thumbprint, the fatty acids on your finger will be a barrier to peroxide decontamination. It's known that it is a fragile process if anything is occluded, either spore clumps or fatty acids from fingers or whatever. So bioburden control is absolutely essential. Now, in fill-in-like applications in the real world, we need to look at the sections that are VHP'd and those that may be just manually disinfected, and how we control that between that. Where the autoclave is, how we get microbiological plates in and out of these lines for a campaign. And here we have a solution of a rapid decon 30-minute cycle with VHP, just to do the outside of agar plates. At the same time, they do the rapid decon, the rapid transfer canisters, rapid transfer port canisters, which can connect into a line at any point to give you delivery and collection of the microbiological growth media plates. And that gives you flexibility and stops the challenge of trying to get, particularly on campaigns, to get materials in and out without compromising the grade A environments. The rapid decon hatch looks like that, and that is based on a 30-minute cycle time. Integrated catalyst, fast and effective distribution, really high turbulence in there to get movement through the loads, point contact presentations, all the things we've learned and all the science that you can have, you can get these rapid cycles if you do the right things. It's just science. Some biologicals are even sensitive down to, the recent one we found was 30 parts per billion. 30 parts per billion. So we need to get cycles down to 30 parts per billion now, and that's always possible. You can aerate for a day or a week or 2 weeks, and you're always going to get down to the very low levels. That's not production. We need to get down in 4 hours, 6 hours. We need to be able to do it in a sensible amount of time. This means simple maths. The more peroxide I put into the system, the more time it is to get out. The more materials there are in there that are absorbent, the more time it is to get out. Plus, we also need to understand the characteristics of even glass has a water barrier, and peroxide with its hydrogen bonding characteristics will bond to that, will bond to stoppers, will absorb from materials. So we've had to develop analytical chemistry now to really support that. And this was pioneered by Genentech, but the use of Amplex Red, which is a fluorescence-based technology, you can look at dissolution, transfer residuals from the gas phase into dissolution at the ppb level. And there's 10, 15 parts per billion is the limit of detection, which is below what the most sensitive biologicals, which it needs to be. Now, we have to look at that from different types of presentations. So if you have a presentation like this, so here's a larger surface area under the unidirectional airflow and a large volume of fill. So the transfer dilution from the gas phase into that is very different to a 0.2 ml fill in a very small vial with a very small neck. So the transfer residuals you need to find in study with the Amplex Red method, and that will then can be spiked into your product to look at the impact on the product. You also need to study, and we use Picaro gas instruments to look at the ppm, ppb levels of peroxide concentration, because there's a free radical attack phase before the transfer residuals take on. You also need to understand and study. And what that means is what's coming off materials in locality, whatever. After the surprise to my microbiologists, they were going to be trained in working a scanning electron micrograph. The next surprise was a couple of them. You're going to be trained in analytical chemistry. So we have this in our lab in Germany, this analytical chemistry for horseradish peroxidase. And one of the microbiologists, now chemist, is she's got quite an open mind, and it's quite interesting to work with the young there, so eager to learn and use new technologies. Fundamentally, that's almost a full-time activity now. So in summary, vapor and fog, but all these processes are different. have different mechanisms, or they may use the same hydrogen peroxide agent, and in the end, hydrogen peroxide has certain characteristics of hydrogen bonding, but a dynamic process and a static process of deposition is very different. The efficacy data needs to be supported by peer-reviewed references, and that needs to be built over time. I'll end my presentation the same way as Tim ended his. Philip invited us here today, and this new technology of enzyme indicators, can that be interesting to these technologies? Of course it can. To be able to make more efficient the cycle development process and to characterize the efficacy in different locations is really important. But we don't live in a world of relative luminescence unit numbers. We live in a world of log efficacy, characterized by biological log reduction, and that's from biological indicators. So we're not going to get rid of biological indicators because we're always going to have those as the reference and correlate these new instruments too. But when we built up the correlation data and we've seen it scalable, then there's an opportunity here. First, to use it as a tool to speed up validation alongside biological indicators, and years to come, maybe, who's to say, maybe replacing. But for the time being, it's just about getting correlation and bringing it alongside. Understanding where your accepted boundaries are and managing those risks, and if you limit the droplets to not being able to get through a HEPA filter, and a HEPA filter never being just the surface, are you really decontaminate that HEPA filter? Big question there. So in a fill-in line, is that really the right application? Absolutely. In a room situation, I think is great technology. You know, VHP is a great technology in rooms, but it's quite difficult to integrate. Dry fog, solid fog, whatever you like to call it, scan fog, is fantastic in rooms. In the very complex surfaces, because the one study that was done in comparison with head-to-head with hydrogen peroxide that is published was this distribution problem of these large molecules that get in underneath sort of surfaces, the far corners. That was the one study that showed these large molecules have a bit more of a distribution challenge and need a little bit of pull push. But the free radical attack mechanism is so powerful, so fast, and the breaking down to really water and oxygen means that I don't see even today hydrogen peroxide replaced in very short order. So it's about understanding the science more and more, sharing the knowledge more and more, and managing the limitations. And then we'll be able to use it in our processes effectively. Thank you very much.
Does anybody have any questions for James? No questions? Okay. Oh, sorry, Martin.
Thank you, Martin.
Thank you very much. It was a nice presentation. Really appreciate all the scientific approach. I have two kind of things that interest me. One, this SEM pictures of the bioindicators. Yep. Do you really think it has some sort of valid information? Because we know these claims will always happen in any lot of biological indicators. And we know that as soon as you look at the biological indicator, you destroy it. You cannot measure all of the biological indicators, right? It's destructive method. So okay, maybe you get information. There are some claims, but we actually know. And just to follow on that, this brings us to this problem of kind of overkill cycles, right? Yeah. This is exactly what my presentation was very like on top, but this using the BI as a tool, not as a target of the process, if you could maybe a little bit extend on this, it would be maybe interesting for the audience here. Thank you.
The first thing about the using SCM analysis. Now, as I said to you, we have microbiologists that are looking at these, so we would target the edge of the biological indicators where classically the spore clumping is. This is about use as a pre-use qualification, but it's really to see the distribution on the biological indicators, which are more than the classical clumping we expect to see. And when you get such mass clumping on biological indicator, it is not usually a rogue on one or two, it is on a lot. So this is about, if you like, pre-use qualification of the lot. You're never going to be finding a rogue BI in an SEM analysis. That would be probability very, very high to do that, because you've only got a small sample number. But to actually pre-qualify as a lot, and I recommend you use it, because essentially we found that now we've applied this process, we don't have qualification challenges that have come up because we're getting unexpected positives. We've had no problems before. It normally comes back, if you do an SEM analysis on those BIs that have used in that cycle, you'll see all sorts of problems. Have a look in the beginning, rule them out. But you have to have a setup to be able to do that. We have a sample of 100 BIs that come from MESA to accept the lot for release or not. So we reserve the lot. We don't buy everything and then try to send them back because they don't want to know about that. So it's about managing that process. On the second one, you're absolutely right. How many levels of overkill do we actually need? And this is one that I'm really don't like. We should be applying overkill based on data and science and not on let's double something. Let's add 50% for no good reason. Why 50%? Why not 49 or 52 or 10? Or what's the value? What's the science behind that? You really have to understand where the edges, and that's where I think the EIs can come in to help a little bit. Because if we can understand the different efficacy in the different locations, we can start to apply where we can study where we're getting the inactivation of the BIs, to 6-log reduction, and then we can start to look at the process variables, because we've got the efficacy, we've got the kill in that location, so how much more do I need to add on? I need to add on what will cover the process variables. I don't need to add on any more than that. And what are the process variables? They will be temperature and humidity. They will be, and that's by calculation, you can derive that. Temperature is worst case, dries is worst case. More peroxide is needed to get to condensation or dew point. If it's hotter, again, the same. That needs to be known. Gas distribution, though the areas that have the most challenging gas distribution, that's a worst case location. That's not a variable. Different surfaces of efficacy on different materials, that is a variable. So we need to be able to cover what the worst case type of materials are, but that's knowledge and data that's well out there. And it just understanding what are the process of variables and applying overkill on that basis. No more, and that's all you need. And classically, process for process. If the buyer burden is really low, now I'll challenge you here, we've got a pre-sterilized container coming from a sterilization process, which is in a single bag, and it's in a, what's the buyer burden going to be on that? And do I really need 12-log reduction? No, you don't. So it speaks for itself. Do the industry want the assurance and the confidence of 12-log reduction? Yes, they do. But if you actually challenge them, do they need that? Is the science behind it? No, it's not, is it? Any more questions? Thank you.
Just wanted to go back to your comment at the beginning of the presentation on the Annex 1 expectations.
Yeah.
With the changes that are due to come up and not recognising VHP gassing, what are the sort of expectations and challenges that companies will see with that? So my company's just looking to introduce isolator technology for powder filling. And where does that kind of leave us with new technologies?
Essentially, if you're into sterols, and if it's a sterile powder, then any of these product contact surfaces require sterilisation. And the issue is, from the regulatory perspective, because in an isolator, there's a lot that just requires disinfection. They've taken out the word sanitisation in the revised Annex 1, and I'm glad you reminded me on that, because I wanted to do a last sales pitch on PHSS conference on Annex 1 to finish off. But that is an expectation, what I'm talking about, for the target areas that require to be product contact. That is the stopper bowl, the trackways, and the chutes and that sort of thing. The rest of it is just disinfection of the barrier, the gloves, and all those, because those are non-contact parts. So that's classical, just 6-log reduction and whatever. The others need to have, and we've turned the words around. You'll see in Annex 1 the new term that's introduced. We all know sterility assurance as a metric, a 6-log reduction of overkill. But assurance of sterility is data-based evidence that the sterility hasn't been compromised. And that's what we need to build up, and that's about understanding the bioburden. There will be bioburden studies that will have to be done on that transfer, Tyvek removal, shut and door and BHP process. What are the bioburden before you start? Now we'll have to do characterization studies on all of that. So that would be the sort of impact that you'd have to do. But the rest of it's just disinfection. There's no question about that. That just needs good classical validation approach on disinfection of an isolator or barrier or material surfaces. That's not going to change.
Okay, thank you.
Thank you. So, last pitch. PHSS next conference. We do have 2 major conferences a year. The sterile challenges of sterile product manufacturing in June, which will be up in Manchester, and the UCL School of Pharmacy collaboration, which is our annual conference in September. Both are free of charge to members. The Annex 1, we have on the 12th of March, coming up very soon, a conference with the regulatory authorities and the industry. And there's going to be about 160 of us at the moment signed up for this, and there's about 20 spaces left, the last I heard, which we're filling up fast. So if you do want to fit into this, it's a real opportunity to understand what the industry concerns are with this draft that's coming. So I do recommend you try and fill one of those last 20 places if you can. It's a big, great opportunity. That's before the 20th of March deadline when comments go back to the... and you will see really the headline of all the main comments. And there's quite a few major industry platforms that have used the PHSS this year for their contributions in comments, which are going to the European Medicines Agency. Big companies have used us now. So we will have a lot of collective headlines of what the main areas of commentary are. It's a challenging document. There's a lot of comments. So, bit to do there.
James, a question. How often do you recommend to do the chamber with gassing, and how often do you recommend to do the chamber plus the HEPA filters? Is there a difference between these two?
The chamber and the HEPA filters, if you're looking at taking that on, that's a material transfer chamber, and that's a cycle with HEPA filters included, and what's actually the process that you're doing here. So the process you're doing here is you're decontaminating some materials that are transferring into another place where you'll decontaminate the materials, that's your target. You've got to make sure that the environment that has been decontaminated isn't going to recontaminate those materials after they've been decontaminated. So the transfer process out. So classically, a very rapid cycle is the load and the transfer chamber up to the barrier of the HEPA filter, and no more than that because it keeps the transfer time down. But the system cycle, as we call it, with a HEPA filter, that is something that should be done after there's been an intrusion into the system, either for the 6-monthly shutdown for calibrations, when things have been opened up. On first installation, absolutely, and then 6-monthly thereafter. And that's normally the sort of approach that's taken, because it's basically down to recontamination of what something is being already decontaminated and not open to contamination again after those routine cycles. So.
Thank you. That also means that the running time or the sterilization time is shorter normally.
For loads, absolutely.
Yeah.
Target the load, target what you're trying to decontaminate. It's not staying in there, it's not processed in there, it's transient through there. And you will prove very easily that will be effective to do that.
Thank you very much.
No problem.
Okay, any more questions for James before I have a go? All done? Great.
Thank you.
Thank you, James.